Hello everyone, this is an audio recorded lecture for visually impaired students from 11th class NCERT unit number 9 named hydrocarbons. Hydrocarbons are the important source of energy. The term hydrocarbon is self-explanatory, which means compound of carbon and hydrogen only. Hydrocarbons play a key role in our daily life. You must be familiar with the term LPG and CNG used as fuels. LPG is the abbreviated form of liquefied petroleum gas, whereas CNG stands for compressed natural gas. Another term, LNG, liquefied natural gas, is also in use these days. This is also a fuel and is obtained by liquefaction of natural gas. Petrol, diesel, and kerosene oil are obtained by the fractional distillation of petroleum found under the earth crust. Coal gas is obtained by the destructive distillation of coal. Natural gas is found in upper strata during drilling of oil wells. The gas after compression is known as compressed natural gas. LPG is used as a domestic fuel with the least pollution. Kerosene oil is also used as a domestic fuel, but it causes some pollution. Automobiles need fuels like petrol, diesel, and CNG. Petrol and CNG operated automobiles cause less pollution. All these fuel contains mixture of hydrocarbons which are source of energy. Hydrocarbons are also used for the manufacture of polymers like polythene, propene, polystyrene, etc. Higher hydrocarbons are used as solvents for paints. They are also used as the starting material for manufactures of many dyes and drugs. Thus, you can well understand the importance of hydrocarbons in your daily life. In this unit, you will learn more about hydrocarbons. Classifications. Hydrocarbons are of different types depending upon the type of carbon carbon bond presents. They can be classified into three main categories: first, saturated; second, unsaturated; and third, aromatic hydrocarbons. Saturated hydrocarbons contain carbon carbon and carbon hydrogen single bonds. If different carbon atoms are joined together to form open chain of carbon atoms with single bond, they are termed as alkanes, as you have already studied in Unit 8. On the other hand, if carbon atoms form a closed chain or a ring, they are termed as cycloalkanes. Unsaturated hydrocarbons contain carbon carbon multiple bonds, double bonds, triple bonds, or both. Aromatic hydrocarbons are a special type of cyclic compounds. You can construct a large number of models of such molecules of both types, open chain and closed chain, keeping in mind that carbon is tetravalent and hydrogen is monovalent. For making models of alkanes, you can use toothpicks for bonds and plasticine balls for atoms. For alkenes, alkynes, and aromatic hydrocarbons, spring models can be constructed. Alkanes, as already mentioned, that alkanes are saturated open chain hydrocarbons containing carbon carbon single bond. Methane is the first member of this family. Methane is a gas found in coal mines and marshy places. If you replace one hydrogen atom of methane by carbon and join the required number of hydrogen to satisfy the tetravalence of the other carbon atom, what do you get? You get C6H6. This hydrocarbon with molecular formula C6H6 is known as ethane. Thus, you can consider C2H6 as derived from CH4 by replacing one hydrogen atom by CH3 group. Go on constructing alkanes by doing this theoretical exercise, that is replacing hydrogen atom by CH3 group. The next molecule will be C3H8C4H10. CH4 arrow replaces any H by CH3 group, gives out CH, C2H6, or we can represent it as C bond, and hydrogens are attached to both carbon atoms. These hydrocarbons are inert under normal condition as they do not react with acids, base, or the other reagents. Hence, they were earlier known as paraffins, Latin param, nature, affines, affinity. Can you think of The general formula for alkanes family or homologous series. If we examine the formula of different alkanes, we find that the general formula for alkanes is CnH2n plus 2. It represents any particular homologue when n is given appropriate value. Can you recall the structure of methane? According to Vesper theory, methane has a tetrahedral structure in which carbon atom lies at the center and four hydrogen atoms lies at four corners of a regular tetrahedron. All CH bonds angles are of 109.5 degree. In alkanes, tetrahedra are joined together with carbon-carbon and carbon-hydrogen bond lengths are 154 pm and 112 pm respectively. You have already read that carbon-carbon and carbon-hydrogen sigma bond are formed by head-on overlapping of sp3 hybridide orbitals of carbon and one s orbital of hydrogen atom. Nomenclature and isomerism. You have already read about nomenclature of different classes of organic compounds in Unit 8. Nomenclature and isomerism in alkenes can further be understood with the help of a few more examples. Common names are given in parentheses. First three alkanes, methane, ethane, and propane, have only one structure, but higher alkanes have more than one structure. Let us write structure for C4H10. Four carbon atoms of C4H10 can be joined either in a continuous chain or with a branch chain in the following two ways. First, carbon atoms in a long straight chain and then hydrogen atoms attached with all carbon atoms. We name it as butane or N-butane. Second, three carbon atoms in a straight chain and one carbon is attached to the second carbon of the straight chain and then we put hydrogen on all carbon atoms. We can name it as 2-methyl-propane or isobutane. In how many ways you can join 5 carbon atoms and 12 hydrogen atoms of C5H12? They can be rearranged in three ways. First, all carbon atoms in a straight chain and then hydrogen atoms get attached to all straight chain carbon atoms. We can name it as pentane or N-pentane. Next, four carbon atoms in a straight chain and one carbon with three H atoms attached to second carbon atom of the second straight chain. We can name it as 2-methyl-butane or isopentane. Next, three carbon atoms in a straight chain and two carbon atoms with six hydrogen atoms attached to the second carbon atom of the straight chain. We can name it as 2,2-dimethyl-propane or neopentane. Structure first and second possesses same molecular formula but differ in their boiling points and other properties. Similarly, structure third, fourth and fifth possesses the same molecular formula but have different properties. Structure first and second are isomers of butane, whereas structure third, fourth and fifth are isomers of pentane. Since difference in properties is due to difference in their structure, they are also known as structural isomers. It is also clear that structure first and third have continuous chain of carbon atom, but structure second, fourth, and fifth have a branch chain. Such structural isomers, which differs in chain of carbon atoms, are also known as chain isomers. Thus, you have seen that C4H10 and C5H12 have 2 and 3 chain isomers respectively. Based upon the number of carbon atoms attached to a carbon atom, the carbon atom is termed as primary, secondary, tertiary, or quaternary. Carbon atom attached to no other carbon atom, as in methane, or to only one carbon atom, as in ethane, is called primary carbon atom. Terminal carbon atoms are always primary. Carbon atom attached to two carbon atom is known as secondary. Tertiary carbon is attached to three carbon atoms and neo or quaternary carbon is attached to four carbon atoms. Can you identify 1, 2, 3, and 4 carbon atoms in structure first to fifth? If you go on constructing structures for higher alkanes, you will be getting still larger number of isomers. C6H12 has got 5 isomers. C6H14 has got 5 isomers and C7H16 has 9. As many as 75 isomers are possible for C10H22. In structure second, fourth and fifth, you observe that CH3 group is attached to carbon atom numbered as 2. You will come across groups like CH3, C2H5, C3H7, etc. attached to carbon atoms in alkanes or other classes of compounds. These groups or substitutes are also known as alkyl group as they are derived from alkanes by removal of one hydrogen atom. General formula for alkyl group is CnH2n plus 1. Let us recall the general rules for nomenclature already discussed in Unit 8. Nomenclature of a few organic compounds: CH3, CH, CH2, CH, CH2, CH3. CH3 attached to second carbon atom of straight chain. CH2, CH3 attached to fourth carbon of straight chain. Name as 4-ethyl 2-methyl hexane. Remark: lowest sum and alphabetical arrangement. Second, CH3, CH2, CH2, CH, CH, C, CH2, CH3. Third, on third carbon atom, CH2, CH3, CH2, CH3. On fourth carbon atom, CH3. On fifth carbon atom, CH, CH3, CH3. Name as 3,3-diethyl 5-isopropyl 4-methyl octane. Remark: lowest sum and alphabetical arrangement. CH3, CH2, CH2, CH, CH, CH2, 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 CH3. On fifth carbon atom, CH3, CH, CH2, CH3. On fourth carbon atom, CH, CH3, bracket twice 2. Remark: sec is not considered while arranging alphabetically. Isopropyl is taken as one word. Next, CH3, CH2, 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 CH, CH2, 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 CH3. On fifth carbon atom, CH2, C, CH3, CH3, CH3 is attached. Remark: further numbering of the substituents of the side chain. Next, CH3, CH2, CH, CH2, CH, CH2, CH3. Third number carbon atom, CH2, CH3 is attached. On fifth number carbon atom, CH3 is attached. Name as 3-ethyl 5-methyl heptane. Remark: alphabetical priority order. If it is important to write the correct IUPAC name for a given structure, it is equally important to write the correct structure from the given IUPAC name. To do this, first of all, the longest chain of carbon atom corresponding to the parent alkane is written. Then, after numbering it, the substituents are attached to the correct carbon atom, and finally, valence of each carbon atom is satisfied by putting the correct number of hydrogen atoms. This can be clarified by writing the structure of 3-ethyl to 2-dimethylpentane in the following steps. First, draw the chain of 5 carbon atoms. Give number to carbon atoms. Attach ethyl group at carbon 3 and 2 methyl groups at carbon 2. Fourth, satisfy the valence of each carbon atom by putting requisite number of hydrogen atoms. Thus, we arrive at the correct structure if you have understood writing of structure from the given name. Then we will further proceed. Next, preparation. Petroleum and natural gas are the main source of alkanes. However, alkanes can be prepared by following method from unsaturated hydrocarbons. Dihydrogen gas adds to alkenes and alkynes in presence of finely divided catalysts like platinum, palladium or nickel to form alkanes. This process is called hydrogenation. These metals absorb dihydrogen gas on their surface and activate the hydrogen bond. Platinum and palladium catalyze the reaction at room temperature, but reactively higher temperature and pressure are required with nickel catalyst. Ethene: CH2 double bond CH2 plus H2. reacts in presence of platinum, palladium, nickel, gives us propane. CH3 single bond CH3 propane. CH2 CH double bond CH2 plus H2 in presence of platinum, palladium, nickel gives us propane. CH3 CH2 CH3 propine. CH3 C triple bond CH plus 2H in presence of PT, PD, Ni gives us propane. CH3 CH2 CH3 from alkyl halide. Alkyl halide on reduction with zinc dust and dilute hydrochloric acid gives alkanes. Chloromethane in presence of zinc or H positive give us methane. And HCl chloroethane in presence of zinc and H positive give us ethane. 1 chloropropane plus H2 in presence of zinc H positive give us propane. Second, alkyl halide on treatment with sodium metal in dry ethereal free from moisture solution give higher alkanes. This reaction is known as Wood's reaction and is used for preparation of higher alkanes containing even number of carbon atoms. Bromomethane in presence of dry ether gives us N-butane. Bromomethane in presence of dry ether gives us ethane. From carboxylic acids. Sodium salt of carboxylic acids on heating with soda lime mixture of sodium hydroxide and calcium oxide gives alkanes containing one carbon atom less than the carboxylic acid. This process of elimination of carbon dioxide from a carboxylic acid is known as decarboxylation. Sodium ethanonate CH3COO negative charge Na positive charge plus NaOH in presence of calcium oxide and heat. CH gives us CH4 plus Na2CO3. Kolbe's electrolytic method, an aqueous solution of sodium and potassium salt of a carboxylic acid on electrolysis gives alkane containing even number of carbon atoms at anode. 2 moles of sodium acetate plus 2 moles of water electrolytes gives us CH3 plus 2 moles of carbon dioxide plus H2 gas plus 2 moles of NaOH. The reaction is supposed to follow the following path. First, 2CH3COO negative Na positive sodium acetate reversible reactions gives us 2 moles of CH3 C double bond O single bond O negative plus 2 Na positive at anode. Acetate ion in second step form after losing 2 electrons. Acetate free radical then after processation of free further reaction it gives us methyl free radical. CH3 plus CH3 gives us CH3 in the form of gas at cathode. H2O plus electrons give us OH negative plus H free radical 2H which escape as hydrogen gas. Methane cannot be prepared by this method. Why? Properties. Physical properties. Alkanes are almost non-polar molecules because of covalent nature of carbon-carbon and carbon-hydrogen bonds and due to very little difference of electronegativity between carbon and hydrogen atoms. They possess weak van der Waals forces. Due to the weak forces, the first four members C1 to C4 are gases, C5 to C17 are liquids, and those containing 18 carbon atoms or more solids at 298 Kelvin, they are colorless and odorless. What do you think about solubility of alkanes in water based upon non-polar nature of alkanes? Petrol is a mixture of hydrocarbons and is used as a fuel for automobiles. Petrol and lower fractions of petroleum are used as for dry cleaning of clothes to remove grease stain. On the basis of this observation, what do you think about the nature of greasy substance? You are correct if you saw that grease is non polar, and hence hydrophobic in nature. It is generally observed that in relation to solubility of substances in solvents, polar substances are soluble in polar solvents, whereas the non-polar ones in non-polar solvents, that is like dissolve like. Boiling point of different alkanes are varies, from which it is clear that there is a steady increase in boiling point with increased number of molecular mass. This is due to the fact that the intermolecular van der Waals forces increase with increase of molecular size or the surface area of the molecule. You can make an interesting observation by having a look on boiling points of three isomeric pentanes, with pentane 2-methylbutane and 2,2-dimethylpropane. It is observed that pentane, having a continuous chain of 5 carbon atoms, has the highest boiling point, whereas 2,2-dimethylpropane boil at 282.5 Kelvin. With increase in number of branch chain, the molecule attains the shape of a sphere. This results in smaller area of contact and therefore weak intermolecular forces between spherical molecules, which are overcome at relatively lower temperatures. Chemical properties. As already mentioned, alkanes are generally inert towards acids, base, oxidizing and reducing agents. However, they undergo the following reaction under certain conditions. First, substitution reaction. One or more hydrogen atoms of alkane can be replaced by halogens, nitro group and sulfonic acid group. Halogenation takes place either at at higher temperature or in presence of diffuse sunlight or ultraviolet light. Lower alkanes do not undergo nitration and sulfonation reactions. These reactions, in which hydrogen atom of alkanes are substituted, are known as substitution reactions. As an example, chlorination of methane is given below. Halogenation CH2 plus Cl in presence of sunlight, CH3Cl plus HCl chloromethane. Chloromethane in presence of H which means sunlight, gives us dichloromethane. Dichloromethane in presence of light provides us trichloromethane. Trichloromethane in presence of light provides us tetrachloromethane. It is found that the rate of reaction of alkanes with halogen is fluorine, chlorine, bromine, iodine. Rate of displacement of hydrogen of alkanes is 3 to 1. Fluorination is too violent to be controlled. Iodination is a very slow and a reversible reaction. It can be carried out in presence of oxidizing agents like HiO3 or HNO3. Halogenation is supposed to be proceed by free radical chain mechanisms involving three steps, namely initiation, propagation, and termination as given below. Mechanisms. Initiations. The reaction is initiated by hydrolysis, homolysis of chlorine molecule in the presence of light or heat. The Cl-Cl bond is weaker than the C and CH bond and hence is easiest to break. Propagation. Chlorine free radical attacks the methane molecule and takes the reaction in forward direction by breaking the CH bond to generate methyl free radical with the formula of HCl. CH4 plus Cl plus gives in presence of light CH3 positive plus HCl. The methyl radical thus obtained attacks the second molecules of chlorine to form CH3Cl with the liberation of another chlorine free radical by homolysis of hydraulic member. Hydro homolysis of chlorine molecule CH3 plus ClCl in presence of light provides us CH3Cl plus Cl. The chlorine and methyl free radical generated above repeat steps A and B respectively, and thereby step A chain of reaction and propagation step B, A and B are those which directly give principal products, but many other propagation steps are possible and may occur. Two such steps given below explain how more highly halogenated products are formed. termination. The reaction stops after some time due to consumption of reactant or due to the following side reactions. The possible side chain terminating steps are chlorine plus chlorine free radical provides us chlorine chlorine. CH3 free radical plus CH3 free radical provides CH3 no single bond CH3. H3Cl free radical plus Cl free radical provides us CH3Cl. Though in CH3Cl the one of the products is formed but free radicals are consumed and the chain is terminated. The above mechanisms helps us to understand the reason for formation of ethane as a byproduct during chlorination of methane combustion. Alkanes on heating in presence of air or dioxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. The general composition equation for an alkane is CnH2n plus 2 Cn plus 1 plus Cn plus 1 divided by 2 bracket close O2 gives out n number of carbon dioxide plus n plus 1 number of H2O. Due to the evolution of large number of heat during combustion, alkanes are used as fuels. During incomplete combustion of alkanes with insufficient amount of air or dioxygen carbon black is formed which are used in the manufacture of ink printer ink black pigments and as filters. CH4 gas plus O2 gas in complete combustion gives us C solid form 2 moles of H2O liquid. Controlled oxidation. Alkanes on heating with the regular supply of dioxygen or air at high pressure and in the presence of substitutable catalyst give a variety of oxidation products. 2 moles of CH4 plus O2 in presence of copper 520 Kelvin temperature and 100 atm pressure gives us methanol. CH4O2 gives us in presence of MO2O3 del gives us methanol. 2 moles of CH3 CH3 plus CO in presence of this ethanoic acid plus water. Ordinary alkanes resist oxidation, but alkanes having tertiary H atom can be oxidized to corresponding alcohols by potassium permanganate. 2-methyl propyl in presence of KMnO4 or oxidation gives us 2-methyl propane 2 on isomerization. An alkane on heating in presence of anhydrous aluminum chloride and hydrogen chloride gas isomerize to branch chain alkanes. Major products are given below. Some minor products are also possible. Which can you think of? Minor products are generally not reported in organic reactions. N-hexane in presence of anhydrous AlCl3H Cl gives us 2-methyl pentane, 3-methyl pentane, pentanone. Aromatization. N-alkanes having 6 or more carbon atoms on heating to 773 Kelvin to 10 to 20 atmospheric pressure in presence of oxides of vanadium, molybdenum or chromium spalted over alumina get dehydrogenation and cyclized to benzene and its homologous. This reaction is known as aromatization or reforming. Toluene reacts in presence of Cr2O3 or V2O5MO2O3 at 773 Kelvin 1020 atmospheric pressure. Toluene C7H8 is methyl derivative of benzene. Which alkane do you suggest for preparation of toluene? Reacts with steam. Methane reacts with steam at 1273 Kelvin in the presence of nickel catalyst to form carbon monoxide and dihydrogen. This method is used for industrial preparation of dihydrogen gas. CH4 plus H2IO gives us in presence of nickel CO plus CH2. Pyrolysis. Higher alkanes on heating to higher temperature decompose into lower alkanes, alkenes, etc. Such a decomposition reaction into smaller fragments by the application of heat is called pyrolysis or cracking. C6H14 gives a C6H12 plus H2 C4H8 plus C2H6 C3H6 plus C2H4 plus CH3. Pyrolysis of alkanes. Pyrolysis of alkane is believed to be a free radical reaction. Preparation of oil gas or petrol gas from kerosene oil or petrol involves the principle of pyrolysis. For example, docoane, a constituent of kerosene of oil on heating to 973 Kelvin in the presence of platinum, palladium, or nickel gives us a mixture of heptane and hexane. Decoding in presence of PTPD Ni at 973 Kelvin temperature provides us heptane plus pentane plus other products. Conformations. Alkanes contain carbon-carbon sigma bonds. Electron distribution of the sigma molecular orbital is symmetrical around the internuclear axis of the carbon-carbon bond, which is not distributed due to rotation about its axis. This permits free rotation about carbon-carbon single bond. This rotation results into different spatial arrangement of atoms in space, which can change into one another. Such spatial arrangement of atoms, which can be further converted into one another by rotation around a carbon-carbon single bond, are called conformations or conformers or rotamers. Alkanes can thus have infinite number of conformation by rotation around carbon-carbon single bonds. However, it may be remembered that rotation around a carbon-carbon single bond is not completely free. It is hindered by a small energy battery of 120 kilojoule per mole due to weak repulsive interaction between the adjacent bonds. Such a type of repulsive interaction is called toroidal strain. Conformations of ethane. Ethane molecule C2H6 contain a carbon-carbon single bond with each carbon atom attached to three hydrogen atoms. Considering the ball and stick model of ethane, keep one carbon atom stationary and rotate the other carbon atom around the carbon-carbon axis. This rotation results into infinite number of spatial arrangement of hydrogen atom attached to one carbon atom with respect to the hydrogen atom attached to the other carbon atom. These are all conformational isomers. Thus, there are infinite number of conformations of ethane. However, there are two extreme cases. One such conformation in which hydrogen atom attached to two carbon are as close together as possible is called eclipsed conformation, and the other in which hydrogen as far apart as possible is known as staggered conformation. Any other intermediate conformation is called a skew, skew conformation. It may be remembered that in all the conformations, the bond angle and the bond length remains the same. And the staggered conformation can be represented as showers and Newman's projection. Saur's projection. In this projection, the molecule is viewed along the molecular axis. It is then projected on paper by drawing the central carbon-carbon bond as a somewhat long straight line. Upper end of the line is slightly towards right or left hand side. The front carbon is shown at the lower end of the line, whereas the rear carbon is shown as the upper end. Each carbon has three lines attached to it corresponding to three hydrogen atoms. The lines are inclined at an angle of 120 to each other. Saur's projection of eclipsed and staggered conformations of ethane are depicted. Newman projection. In this projection, the molecule is waved at carbon-carbon bond head on. The carbon atom nearer to the eye is represented by a point. Three hydrogen atoms attached to the front carbon atoms are shown by three lines draws at angle of 120 to each other. The rear carbon atom is represented by a circle and three hydrogen atoms are shown attached to it by the shortest line drawn at an angle of 120 to each other. Relative stability of conformations, as mentioned earlier, in staggered form of ethane, the electron cloud of carbon hydrogen bond as apart as possible. Thus, there are minimum repulsive forces, minimum energy, and maximum stability of the molecule. On the other hand, when the staggered form changes into the eclipsed form, the electron cloud of the carbon hydrogen bond came closer to each other during resulting increase in electron cloud repulsion. To check the increased repulsion forces, molecule will have to possess more energy and thus has lesser stability. As already mentioned, the repulsive interaction between the electron cloud which affect the stability of a conformation is called toroidal strain. Magnitude of toroidal strain depend upon the angle of rotation about carbon-carbon bond. This angle is also called dihedral angle of toroidal angle. Of all the conformation of ethane, the staggered form has the least toroidal strain, and the eclipsed form the maximum toroidal strain. Therefore, staggered conformation is more than the eclipsed conformation. Hence, molecule already remains in struggle in a staggered conformation, or we can say that it is preferred conformation. Thus, it may be inferred that rotation around carbon-carbon bond in ethane is not completely free. The energy difference between the two extreme force form is of the order of 12.5 kilojoule per mole, which is very small even at ordinary temperature. The ethane molecule gains thermal or kinetic energy sufficient enough to overcome this energy barrier of 12.5 kilojoule per mole through intermediate intermolecular collision. Thus, it can be said that rotation about carbon-carbon single bond in ethane is almost free for all practical purposes. It has not been possible to separate and isolate different conformation isomers of ethane. Alkenes. Alkenes are unsaturated hydrocarbon containing at least one double bond. What should be the general formula of alkenes? If there is one double bond between two carbon atoms in alkane, there must be two hydrogen atoms less than alkanes. Hence, general formula for alkenes is CnH2, and alkenes are also known as olefins since the first member ethylene or ethene was found to form many oily liquid on reaction with the chlorine. Structure of double bond. Carbon-carbon double bond in alkanes consists of one strong sigma bond due to head-on overlapping of sp2 hybridized orbitals and one weak pi bond obtained by lateral or sideway overlapping of 2p orbitals of the two carbon atoms. The double bond is shorter in bond length than the carbon-carbon single bond. You have already read that the pi bond is a weaker bond due to poor sideways overlapping between the two p orbitals. Thus, the presence of pi bond makes alkenes behave as source of loosely held mobile electrons. Therefore, alkenes are easily attacked by reagents or compounds which are in search of electrons. Such reagents are called electrophilic reagents. The presence of weaker pi bond makes alkenes unstable molecule in comparison to alkanes, and thus alkenes can be changed into single bond compounds by combining with the electrophilic reagent. Strength of the double bond is greater than that of carbon-carbon single bond in ethane. Orbital diagram of ethane molecule. Nomenclature. For nomenclature of alkenes in IUPAC system, the longest chain of carbon atom containing the double bond is selected. Numbering of the chain is done from the end which is nearer to the double bond. The suffix in replaced N of alkenes It may represent it may be remembered that the first member of alkene series is CH2 replacing N by 1 in CnH2 and known as methene but has a very short life as already mentioned. First stable member of alkene series in C2H4 known as ethylene or ethene. IUPAC name of a member of alkenes CH3 CH double bond CH2 propene CH3 CH2 CH double bond CH2 butene CH3 CH double bond CH double bond CH3 butene isomerism. Alkenes show both structural isomerism and geometrical isomerism. Structural isomerism as in alkanes ethene C2H4 and propene C3H6 can have only one structure, but alkanes higher than propene have different structure. Alkene possessing C4H8 as molecular formula can be written in the following way. But1 in CH2 double bond CH single bond CH2 CH3. But2 in CH3 CH double bond CH CH3. But2 in 2 methyl prop 1 in CH2 double bond C CH3 no, CH3. Structures first and third and second and third are the example of chain isomerism which are the mangena, whereas example of chain isomerism whereas structure first and second are position isomers. Geometrical isomers. Doubly bonded carbon atom have to satisfy the remaining two valencies by joining with two atoms or groups. If the two atoms or groups attached to each carbon atom are different, they can be represented by YXC double bond CXY like structure. YXC double bond CXY can be represented in space as C double bond C X Y X Y C double bond C X Y Y X. In A, the two identical atoms, that is, both the X or both the Y lies on the same side of the double bond. But in B, the two X or two Y lies across the double bond or on the opposite sides of the double bond. This results in different geometry of A and B, that is, disposition of atoms or group in space in the two arrangements is different. Therefore, they are stereoisomers. They would have the same geometry if atoms or the groups around C double bond C bond can be rotated by rotation around C double carbon. Carbon double bond is not free. It is restricted. For understanding this concept, take two pieces of strong cardboard and join them with the help of nails. Hold one cardboard in your hand and try to rotate the other. Can you really rotate the other cardboard? The answer is no. The rotation is restricted. This illustrates that the restricted rotation of atoms or group around the doubly bonded carbon atom give rise to different geometries of such compounds. The stereoisomers of this type of are called geometrical isomers. The isomer of the type in which two identical group of atoms is called cis isomer, and the other isomer of the type B is which identical atom or group lies on the opposite sides of the double bond is called trans isomers. The cis and trans isomer have the same structure but have different configuration due to different arrangement of carbon of atoms or group in space. These isomers differ in their properties like melting point, boiling point, dipole moment, solubility. Geometrical or cis trans isomers of but2 in are C double bond C CH3 H C double bond CH3 H CH3. Cis form of alkene is found to more polar than trans form. For example, dipole moment of cis but2 in is 0.33 by, whereas dipole moment of the trans form is almost zero. It can be said that transbute 2 in is non-polar. This can be understood by drawing geometrics of the two forms are given below, from which it is clear that in the transbute two in the two methyl groups are in opposite direction. Therefore, dipole moments of CH3 bonds cancel, thus making the trans form non-polar. In the case of solid, it is observed that the trans isomer has higher melting point than the cis form. Geometrical or cis trans isomerism is known by alkanes of the two types XYC double bond CXY and XYC is equals to CZW. Preparation from alkynes. Alkynes on partial reduction with calculated amount of dihydrogen in presence of pelletized charcoal, partially deactivated with poisons like sulfur compounds or quinoline, gives alkenes. Partially deactivated pelletized charcoal is known as Lind's catalyst. Alkenes thus obtained are having cis geometry. However, alkenes on reduction with sodium in liquid ammonia form trans alkenes. Alkyne RC triple bond Cr dash plus H2 in presence of PDC cis alkenes. Alkyne plus H2 in presence of Na liquid NH3 trans alkene ethine ethene propine propene will propane thus obtained show geometrical isomerism. Think for the reason in spot of your answer from alkyl halide. Alkyl halide RX on heating with alcoholic potassium hydroxide dissolve in alcohol, say ethanol, eliminated on molecules of halogen acid to form alkenes. This reaction is known as dehallogenation, that is removal of halogen acid. This is example of beta elimination reaction. Since hydrogen atom is eliminated from beta carbon atom next to the carbon to which halogen is attached. Nature of halogen atom and the alkyl group determine rate of the reaction. It is observed that for halogens the rate is iodine, bromine, chlorine, while for alkyl group this is tertiary, secondary, primary. From vicinal dihalide in which two halogen atoms are attached to two adjacent carbon atoms are known as vicinal dihalide. Vicinal dihalide on treatment with zinc metal use a molecules of ZnX2 to form an alkene. This reaction is known as dehalogenation. CH2Br plus Zn gives out CH2 double bond CH2 plus ZnBr2 from alcohol by acidic dehydration. You have read during nomenclature of different homologous series in Unit 12 that alcohol are the hydroxy derivatives of alkenes. They are represented by ROH, where R is CnH2n plus 1. Alcohols on heating with concentrated sulfuric acid form alkenes with the elimination of one water molecule. Since the water molecule is eliminated from the alcohol molecule in presence of an acid, this reaction is known as acidic dehydration of alcohol. This reaction is also the example of beta elimination reaction. Since OH group takes out one hydrogen atom from the beta carbon atom. Properties, physical properties. Alkenes as a resemble alkanes in physical properties except in types of isomerism and difference in polar nature. The first three members are gases, the next 14 are liquids, and the higher one are solids. Ethene is a colorless gas. Ethene is a colorless gas with a faint sweet smell. All other alkenes are colorless and odorless, insoluble in water but fairly soluble in non-polar solvents like benzene, petroleum, ether. They show a regular increase in boiling point with increase in size, that is every CS2 group added by increasing boiling point by 20-30 K. Like alkanes, straight chain alkenes have higher boiling point than isomeric branch chain compounds. Chemical properties. Alkenes are the rich source of a loosely held loosely held pi electrons, due to which they show addition reaction in which the electrophiles add on the carbon-carbon double bond to form the addition product. Some reagents also add by free radical mechanism. There are cases when under special conditions alkenes undergo free radical substitution reaction. Oxidation and ozonolysis reaction are also quite prominent in alkenes. A brief description of different reactions of alkenes is given below. Addition of dihydrogen alkenes add up one molecule of dihydrogen gas in the presence of finely divided nickel, palladium, or platinum, or to form alkanes. Addition of halogen like bromine and or chlorine add up to alkene to form vicinal dihalide. However, iodine does not show addition reaction under normal conditions. The reddish orange color of bromine solution in water tetrachloride is discharged when bromine adds up to an unsaturation site. This reaction is used as a test for unsaturation. Addition of halogens to alkenes is an example of electrophilic addition reaction involving cyclic halonium ion formation, which we'll study in higher classes. Ethene in presence of CCl4 gives out 1,2-dibromomethane. Propene gives us 1,2-dichloropropane. Addition of hydrogen halide CHCl HBr HI adds up to alkenes to form alkyl halide. The order of reactivity of hydrogen halide is HiHBrHCl. Like addition of halogens to alkenes, addition of hydrogen halide is also an example of electrophilic addition reaction. Let us illustrate this by taking addition of HBr to symmetrical and unsymmetrical alkenes. Addition reaction of HBr to symmetrical alkenes. Addition reaction of HBr to symmetrical alkenes take place by electrophilic addition mechanisms. Addition reaction of HBr to unsymmetrical alkenes. How will HBr added to propene? The two possible products are first and second. Markovnikov, a Russian chemist, made a generalization in 1869 after studying such reaction in details. These generalizations led Markovnikov to frame a rule called Markovnikov rule. The rule states that negative part of a addendum gets attached to carbon atoms which possesses lesser number of hydrogen atoms. Thus, according to this rule, product first to bromopropene is expected. In actual practice, this is the principal product of the reaction. This generalization of Markovnikov's rule can be better understood in terms of mechanics of the reaction mechanism. Hydrogen bromide provides an electrophile H positive which attack the double bond to form carbocation. As the secondary carbocation is more stable than the primary carbocation, therefore the former predominates becomes because it is formed at faster rate. The carbocation is attacked by Br negative ion to form the product as follows. Anti-Markovnikov addition or peroxide effect or Kharas effect. In presence of peroxide, addition of HBr to unsymmetrical alkenes like propene take place contrary to the Markovnikov rule. This happens only with HBr, not with HCl and HI. This addition reaction was observed by MS Kharas and Fr. Mayo in 1933 at the University of Chicago. This reaction is known as peroxides or Kharas effect. Addition reaction anti-Markovnikov rule. Mechanism peroxide effect proceeds by free radical chain mechanisms as the secondary free radical obtained in the above mechanism is more stable than the primary. This explains the formation of 1-bromopropane as a major product. It may be noted that the peroxide effect is not observed in addition of HCl and HI. This may be due to the fact that the HCl bond being stronger than HBr bond is not cleavaged by the free. Kaldo ilminate by the free radical, whereas the Hi bond is weaker, and iodine free radicals combine to form iodine molecule instead of adding to the double. Addition of sulfuric acid. Cold concentrated sulfuric acid adds to alkenes in accordance with Markovnikov rule to form alkyl hydrogen sulfate by the electrophilic addition reaction. Addition of water. In presence of few drops of concentrated sulfuric acid, alkenes react with water to form alcohol in accordance with Markovnikov rule. Oxidation. Alkenes on reaction with cold dilute aqueous solution of potassium permanganate Bayer's reagent produce vicinal glycose. Decolorization of KMnO4 solution is used as test for unsaturation. Acidic potassium permanganate or acidic potassium dichromate oxidizes alkenes to ketones or acid depending upon the nature of alkene and the experimental condition. Ozonolysis. Ozonolysis of alkenes involves the addition of ozone molecule to alkene to form ozonide and then cleavage on the ozonide by ZnH2O2 smaller molecule. This reaction is highly useful in detecting the position of the double bond in alkenes or the unsaturated compounds. Polymerization. You are familiar with polythene bags and polythene sheets. Polythene is obtained by the combination of large number of ethene molecule at high temperature, high pressure, and in the presence of catalyst. The large molecules thus obtained are called polymers. This reaction is known as polymerization. The simple compounds from which polymer are made are called monomers. Other alkanes are undergo polymerization. Polymers are used for manufacture of plastic bags, sequence, squeeze bottles, refrigerator dishes, toys, pipes, radio and TV cabinet. Polypropylene is used for the manufacture of milk crates, plastic buckets, and other modular articles. Though these materials have now become common, excessive use of polythene and polypropylene is a matter of great concern for all of us. Alkynes. Like alkynes are also unsaturated hydrocarbons. They contain at least one triple bond between two carbon atoms. The number of hydrogen atoms is still less in alkynes as compared to alkenes or alkanes. Their general formula is CnH2n-2. The first stable member of alkyne series is ethine, which is popularly known as acetylene. Acetylene is used for arc welding purpose in the form of oxyacetylene flame obtained by mixing acetylene with oxygen gas. Alkynes are starting materials for a large number of organic compounds, hence, it is interesting to study this class of organic compounds. Nomenclature and isomerism. In common system, alkynes are named as derivatives of acetylene. In IUPAC system, they are named as derivatives of the corresponding alkanes, replacing "-ane" by the suffix "-ine". The position of the triple bond is indicated by the first triply bonded carbon. Common and IUPAC names of a few members of alkynes. You have already learned that ethine and propyne have got only one structure, but there are two possible structures for butylene, but-1-ine, but-2-ine. Since these two compounds differ in their structure due to the position of triple bond, they are known as position isomers. In how many ways you can construct the structure for the next homolog series, that is the next alkyne with molecular formula C5H8. Let us try to arrange five carbon atoms with a continuous chain and with a side chain. Following are possible ways: CH triple bond C, CH2, CH2, CH3, pent-1-ine, CH3, C triple bond C, CH2, CH3, pent-2-ine, CH3, CH, C triple bond CH, third carbon atom attached to CH3, 3-methyl but-1-ine. Structure first and second are position isomer, and structure first and third or second or third are chain isomers. Structure of triple bond. Ethine is the simplest molecule of alkyne series. Each carbon atom of ethine has two sp hybridized orbital. Carbon-carbon sigma bond is obtained by the head-on overlapping of the two sp hybridized orbital of two carbon atom. The remaining sp hybridized orbital of each carbon atom undergoes overlapping along the internuclear axis with the 1s orbital of each of the two hydrogen atom, forming two carbon hydrogen sigma bonds. HCC bond angle is of 180 degree. Each carbon has two unsaturated unhybridized p orbital which are particular to each other as well as to the plane of the carbon-carbon sigma bond. The two p orbitals of one carbon atom are parallel to the two p orbital of the other carbon atom, which undergo lateral or sideways overlapping to form two pi bonds between two carbon atoms. Thus, ethine molecule consists of two carbon carbon sigma bond, two carbon hydrogen pi bonds, and two carbon carbon pi bonds. The strength of carbon carbon triple bond is more than those of carbon carbon triple bond, carbon carbon single bond. The carbon carbon triple bond length is stronger 120 ppm than those of carbon double bond 133 ppm and carbon 3 carbon carbon single bond 154 pm. Electron cloud between two carbon atoms is cylindrically symmetrical about the internuclear axis. Thus, ethine is a similar molecule. Preparation from calcium carbide. On industrial scale, ethine is prepared by treating calcium carbide with water. Calcium carbide is prepared by heating quicklime with the manana. Quicklime can be obtained by heating limestone as shown in following reaction. CaCO3 in presence of heat CaO plus O2 from vicinal dihalide. Vicinal dihalide on treatment with alcoholic potassium hydroxide undergo dehydrogenation. Dehalogenation. One molecule of hydrogen halide is eliminated to form alkene halide, which on treatment with soda amide gives alkyne. Properties. Physical property of alkyne follow the same trend of alkenes and alkanes. First three members are gases, the next eight are liquid, and the higher ones are solids. All alkynes are colorless. Ethine has a characteristic odor. Other members are odorless. Alkynes are weakly polar in nature. They are lighter than water and immiscible with water but soluble in organic solvents like ether, carbon tetrachloride, and benzene. Their melting point, boiling point, and density increase with increase in molar mass. Chemical properties. Alkynes show acidic nature, addition reaction, and polymerization reaction as follows. Acidic character of alkyne. Sodium metal and sodamide are strong bases. They react with ethine to form sodium acetylide with the liberation of dihydrogen gas. These reactions have not been observed in case of ethine or ethane, thus indicating that ethine is acidic in nature in comparison of ethene and ethane. Why is it so? Has it something to do with their structure and the hybridization? You have read that hydrogen atom in ethine are attached to the sp hybridized carbon atom, whereas they are attached to sp2 hybridized carbon atom in ethene and sp3 hybridized carbon in ethane. Due to the maximum percentage of s character, the sp hybridized orbital of carbon atom in ethane molecule have highest electronegativity. Hence, these attract the shared pair of the carbon hydrogen bond of ethine to a greater extent than that of the sp2 hybridized orbital of carbon in ethene and the sp3 hybridized orbital of carbon in ethane. Thus, in ethine, hydrogen atoms can be liberated as protons more easily as compared to ethene and ethane. Hence, hydrogen atoms of ethine attached to triply bonded carbon atom are acidic in nature. You may note that the hydrogen atom are acidic in nature. You may note that the hydrogen atom attached to the triply bonded carbon are acidic, but not all the hydrogen atoms of alkynes. CH3 CH triple bond CH plus Na gives monosodium ethionide. CH triple bond C negative Na positive half H2. CH triple bond C negative Na positive plus Na gives out Na positive C negative Na positive triple bond C negative Na positive disodium ethionide sodium propanide. These reactions are shown by alkenes and alkanes ensued for distinction between alkynes, alkenes, and alkanes. What about the above reactions with but1-ine and but2-ine? Alkenes and alkynes follow the following trend in their acidic behavior. CH triple bond CH, CH2, single bond CH2, CH3, single bond CH3, CH triple bond CH, CH3, single bond C, CH3, C, CH3, C, triple bond C, CH3. Addition reaction alkynes contains a triple bond, so they add up to molecules of dihydrogen, halogen, hydrogen halide, etc. Formation of addition product takes place according to the following steps. The addition product form depending upon stability of vinylic cation. Addition in unsymmetrical alkynes take place according to Markovnikov rule. Majority of the reactions of alkynes are the example of electrophilic addition reaction. A few addition reactions are addition of dihydrogen CH triple bond CH plus H2 in presence of platinum palladium nickel gives us CH2 double bond CH2. Next reacts with H2 gives us CH3 single bond CH3. Propine plus H2 in presence of platinum palladium nickel gives us propene. Further reaction proceed in presence of H2 gives us propane. Addition of halogen CH3 C triple bond CH plus Br gives us 1,2-dibromopropene. Further reaction proceed in presence of Pr2 gives us 1,1,2,2 tetrabromopropane. Reddish orange color of the solution of bromine in carbon tetrachloride is decolorized. This is used as a test for unsaturation. Addition of hydrogen halides. Two molecules of hydrogen halide add two alkynes to form gem dihalide. CH triple bond CH plus HBr gives us bromoethane. Next, after further reaction proceeding, it provides 1,1-dibromomethane. Addition of water. Like alkanes and alkenes, alkynes are also immiscible and do not react with water. However, one molecule of water adds to alkynes on warming with mercuric sulfate and dilute sulfuric acid CC at 33 Kelvin to form carbonyl compound CH triple bond CH ethine in presence of plus H2O in presence of Hg2 positive H positive at 33 Kelvin temperature provides us CH2 double bond COH. Isomerization. After isomerization it provides us ethanol. Propine in presence of H2 plus H positive 33 Kelvin temperature gives us CH3 C double bond CH2 COH. Isomerization. After isomerization it provides us propanone. Fifth, polymerization. Linear polymerization. Under suitable condition, linear polymerization of ethine take place to produce polyacetylene or polythene, which is a high molecular weight polyene containing repeating units of CH double bond CH single bond CH double bond CH and can be represented as bracket bond continue CH double bond CH double bond CH up to N. Under special conditions, this polymer conducts electricity. Thin film of polyacetylene can be used as electrodes in battery. These films are good conductor, lighter and cheaper than the metal conductor. Cyclic polymerization. Ethane on passing through red hot iron tube at 873 Kelvin undergoes cyclic polymerization. Three molecule polymerize to form benzene, which is the starting molecule for the preparation of derivatives of benzene, dyes, drugs, and large number of other organic compounds. This is the best route for entering from aliphatic to aromatic compounds as discussed. Aromatic hydrocarbons. These hydrocarbons are also known as arenes since most of them possesses pleasant odor. The class of compounds was named as aromatic compound. Most of such compounds were found to contain benzene ring. Benzene ring is highly unsaturated, but in a majority of reactions of aromatic compound, the unsaturation of benzene ring is retained. However, there are examples of aromatic hydrocarbons which do not contain a benzene ring but instead of contain other highly unsaturated ring. Aromatic compounds containing benzene ring are known as benzenoids, and those not containing a benzene ring are known as non-benzenoids. Some examples of arenes are benzene, toluene, naphthalene, biphenyl. Nomenclature and isomerism. The nomenclature and isomerism of aromatic hydrocarbons has already been discussed in Unit 10. All six hydrogen atoms in benzene are equivalent so that it forms one and only one type of monosubstituted product. When two hydrogen atoms in benzene are replaced by two similar or different monovalent atoms or groups, three different position isomers are possible. The 1, 2, or 1, 6 is known as the ortho, and 1, 3, 1, 5 known as meta, and 1, 4 as para. A substituted compound. A few examples of derivatives of benzene are methylbenzene, 1, 2 dimethylbenzene. Structure of benzene. Benzene was isolated by Michael Faraday in 1826. The molecular formula of benzene is C6H6, indicates a high degree of unsaturation. This molecular formula did not account for its relationship to corresponding alkanes, alkenes, and alkynes, which you have studied in earlier section of this unit. What do you think about its possible structure? Due to these unique properties and unusual stability, it took several years to assign its structure. Benzene was found to be stable, more molecule and found to form a triazolide, which indicates a presence of three double bonds. Benzene was further found to produce one and only one monosubstituted derivative, which indicates that all the three 6 and 6 carbon and 6 hydrogen atoms of benzene are identical. On the basis of this observation, August Kekulé in 1865 proposed the following structure for benzene, having cyclic arrangement of 6 carbon atom with alternate single and double bonds and one hydrogen atom attached to each carbon atom. The calculus structure indicates the possibility of two isomeric 1,2-dibromobenzene in one of the isomer. The bromine atom are attached to doubly bonded carbon atom, whereas in other they are attached to the singly bonded carbons. However, benzene was found to form only one orthodistributed product. This problem was overcome by Kekulé by suggesting the concept of oscillating nature of double bonds in benzene. Even with the modification, Kekulé structure of benzene fails to explain unusual stability and preferences to substitution reaction than addition reaction, which could later on be explained by resonance. Resonance and stability of benzene. According to valence bond theory, the concept of oscillating double bond in benzene is now explained by resonance. Benzene is a hybrid of various resonating structures. The two structures A and B given by Kekulé are the main contributing structures. The hybrid structure is representing by inserting a circle or a dotted circle in the hexagon as shown. The circle represents the six electrons which are delocalized between the six carbon atoms of the benzene ring. The orbital overlapping gives us better picture about the structure of benzene. All the six carbon atoms in benzene are sp2 hybridized. Two hybridized orbitals of each carbon atom overlap with two sp hybridized orbitals of adjacent carbon atom to form six carbon-carbon sigma bond, which are in the hexagonal plane. The remaining sp2 hybrid orbitals of each carbon atom overlaps with s orbital of hydrogen atom to form six ch sigma bond. Each carbon atom is now left with one unhybrid p orbital perpendicular to the plane of the ring. The unhybrid p orbital of carbon atom are close enough to form a pi bond bilateral overlap. There are two equal possibilities of forming three pi bonds by overlap of p orbitals of C1, C2, C3, C4, C5, C6 or C2, C3, C4, C5, C6, C1 respectively. The internuclear distance between all carbon atoms in the ring has been determined by the X-ray diffraction to be the same. There is equal probability for the p orbital of each carbon atom to overlap with the p orbital of adjacent carbon atom. This can be represented in form of two donuts of electron cloud, one above and one below the plane of hexagonal ring. The six pi electrons are thus delocalized and can move freely about the six carbon nuclei instead of any two. The delocalized pi electron cloud is attracted more strongly by nuclei of carbon atoms than the electron cloud localized between two carbon atoms. Therefore, presence of delocalized pi electron in benzene makes it more stable than the hypothetical cyclohexatriene. X-ray diffraction data reveals that benzene is a planar molecule. Had any one of the above structure of benzene been correct, two types of carbon-carbon bond lengths were expected. However, X-ray data indicates that all the six carbon-carbon bond lengths are of same order, which is intermediate between single bond and carbon-carbon double bond. Thus, the absence of pure double bond in benzene accounts for the reluctance of benzene to same show addition reactions under normal conditions, thus explaining the unusual behavior of benzene. Aromaticity. Benzene was considered as parent aromatic compound. Now the name is applied to all the ring systems, whether or not having benzene ring processing following characteristic: planarity, complete delocalization of pi electrons in the ring, presence of 4n plus 2 pi electrons in the ring where n is an integer. This is often referred as Huckel rule. Some example of aromatic compound are benzene, cyclopentadiene, naphthalene, anthracene, phenanthracene. Preparation of benzene. Benzene is commercially isolated from coal tar. However, it may be prepared in laboratory by following method: cyclic polymerization of ethine, decarboxylation of aromatic acid, sodium salt of benzene acid on heating with soda lime gives benzene. Reduction of phenol. Phenol is reduced to benzene by passing its vapor over heated zinc dust. ठीक है. Physical properties. Aromatic hydrocarbons are non-polar molecules and are usually colorless liquids of solid with a characteristic aroma. You may also familiar with naphthalene balls, which are used in toilets and for preservation of clothes because of unique smell of the compound and the mouth repellent property. Aromatic hydrocarbons are immiscible water, but are readily miscible with organic solvent. They burn with sooty flame. Chemical properties. Arenes are characterized by electrophilic substitution reaction. However, undergo under special conditions, they can also undergo addition and oxidation reaction. Electrophilic substitution reaction. The common electrophilic substitution reaction of arenes are nitration, halogenation, sulfurylation, Findercraft alkylation, acylation reaction, in which attacking reagent is an electrophile. Nitration. Nitrogen gas is involved because A nitro group is introduced into benzene ring when benzene is reacted with a mixture of concentrated nitric acid and concentrated sulfuric acid. Nitrating mixture. Hallucination. Arenes react with halogen in presence of Lewis acid like anhydrous FeCl3, FeBr or AlCl3 to yield haloarenes. Sulfonation. The replacement of a hydrogen atom by sulfonic acid group in a ring is called sulfonation. It is carried out by heating benzene with fuming sulfuric acid. Rindercraft alkylation reaction. When benzene is treated with an alkyl halide in presence of anhydrous aluminum chloride, alkyl benzene is formed. Why do we get isopropyl benzene on treating benzene with 1-chloropropane instead of an propyl benzene? Rindercraft acylation reaction. The reaction of benzene with an acyl halide or acid anhydride in presence of Lewis acid yields acyl benzene. If excess of electrophilic reagent is used, further substitution reaction may take place in which other hydrogen atoms of benzene ring may also be successively replaced by the electrophile. For example, benzene on treatment with excess of chlorine in the presence of anhydrous AlCl3 can be chlorinated to hexachlorobenzene C6Cl6. Mechanism of electrophilic substitution reaction. According to experimental evidences, S equal to substitution, A equal to electrophilic reaction are supposed to proceed by the following three steps: generation of electrophile, formation of carbocation intermediate, removal of proton from carbocation intermediate. Generation of electrophile E positive. During chlorination, alkylation, and acylation of benzene anhydrous AlCl3 being a Lewis acid helps in generation of electrophile Cl positive, R positive, Rc positive, or respectively by combining with the attacking reagent. Step 1 and Step 2. Formation of carbocation. Attack of electrophile result in the formation of sigma complex or arenium ion in which one of the carbon is sp3 hybridized. The arenium ion gets stabilized by resonance. Sigma complex or arenium ion loses its aromatic character because of delocalization stops at sp3 hybridized carbon. Removal of proton. To resonate, restore the aromatic character, sigma complex releases proton from sp3 hybridized carbon on attack by AlCl4 negative and HSO4 negative. Addition reaction under vigorous conditions, that is at high temperature or pressure in presence of nickel catalyst, hydrogenation of benzene gives cyclohexane. Under ultraviolet light, three chlorine molecules add to benzene to produce benzene hexachloride C6H6Cl6, which is also called gamma hexane. Combustion. When heated in air, benzene burns with duty flame, producing carbon dioxide and water. General combustion reaction for any hydrocarbon may be given by the following chemical equation: CXHY plus X plus Y by 4 into O2 gives out X moles of carbon dioxide plus Y by 2 H2O. And directive influence of a functional group in monosubstituted benzene. When monosubstituted benzene is subjected to further substitution, three possible disubstituted products are not formed in equal amounts. Two types of behavior are observed: either ortho and para products or meta products is predominantly formed. It has also been observed that this behavior depends on the nature of substituent already present in benzene ring and not on the nature of the entering group. This is known as directive influence of substituents. Reason for ortho, para, or meta directing nature of groups are discussed below. Ortho and para directing groups. The groups which direct the incoming group to ortho and para positions are called ortho and para directing groups. For example, let's discuss the directive influence of phenolic acid. Phenol is resonance hybrid. It is clear from about the resonating structure that the electron density is more on earth and para position is the substitution takes place mainly at these positions. However, it may be noted that minus I effect of the minus OH group also operates, due to which the electron density on ortho and para positions of the benzene ring is slightly reduced, but the overall electron density increase at this position of the ring due to resonance. Therefore, OH negative group activates the benzene ring for the attack by an electrophile. Other example of activating groups are NH2, NHR, NHCO, CH3, OCH3, CH3, C2H5, etc. In the case of aryl halide, solutions are moderately deactivating because of their strong minus I effect. Overall electron density on benzene ring decreases. It makes further substitution difficult. However, due to resonance, the electron density on ortho and para position is greater than that of meta position, since they are also ortho and para directing groups. Resonance structure of chlorobenzene. Meta directing groups. The group which direct the incoming group to meta position are called meta directing groups. Some examples of meta directing groups are NO2, CN, CHO, COR, COOH, COO, or SO3H. In this case, the overall electron density on benzene decreases, making further substitution difficult. Therefore, these groups are called deactivating group. The electron density on ortho and para position is comparatively less than that of at meta position, since the electrophile attack on comparatively electron rich meta positive, resulting in meta substitution. Carcinogenicity and toxicity. Benzene and polynuclear hydrocarbons containing more than two benzene rings fused together are toxic and said to possess cancer producing properties. Such polynuclear hydrocarbons are formed on incomplete combustion of organic materials like tobacco, coal, and petroleum. They enter into human body and undergo vigorous biochemical reactions and finally damage DNA and cause cancer. Some of carcinogenic hydrocarbons are 1,2 benzoanthracene, 3-methyl cholanthrazine, 1,2 benzypyrene, etc.